we have sound, we have picture. Okay. Unsaturated solution. We've actually talked about a lot of these concepts before, but I just wanted to formalize some stuff. An unsaturated solution is a solution that contains less than the maximum amount of dissolved solute. So if you have undissolved solute present, and there should be an and there, I need to fix that. That and is actually really important. And the system is not yet at equilibrium, then the rate of, this should say then the rate of dissolving is greater than the rate of precipitation or recrystallization. And if you think about it, that has to be the case, because if it is not yet saturated, if we are unsaturated, then more will continue to dissolve. And if the two rates were equal, if we had just as much reprecipitating, then you wouldn't get any more dissolving. So the rate of dissolving has to be faster than the rate of recrystallization. So these are for unsaturated solutions. So if you look at the little picture here, the solution is not yet full. Of dissolved particles. And you can see we have 1, 2, 3, 4, 5 arrows going up and only 1 arrow going down. So that shows dissolving faster than recrystallization. Consider the following. You toss some solute into the solvent, and at the moment you put it in, what is the rate of dissolving like? So we put solute into solvent. In the moment you put it in, what's the rate of dissolving like? Rate of dissolving is high or low? High. What is the rate of recrystallization like? 0, because we don't have any dissolved yet, right? Not at that moment at 0, time equals 0. And what's going to happen to those two rates as time goes on? They're going to come together in the middle. And that point right there is the point of saturation. So at the start, you have a very high rate of the forward reaction and none of the reverse reaction because there's nothing here yet. And this is part way to saturation. And the concentration of ions will continue to increase until either you run out of solid solute, and if that were the case, I don't think you'll ever have to draw a graph like this, but your graph for this one would look like your dissolving, recrystallizing, dissolving, 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 dissolving. Oh, we ran out of solute. Recrystallizing, la, 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 la. Oh, we ran out of solute. And if we run out of solute at that point, what's happened to the rate of dissolving? You now have no more solute. You got nothing over here. You can't go forward because there's no more solute, no more solid, nothing there. What happens to the rate of dissolving when you have nothing left to dissolve? 0. Bam. And then it'll just flatline. There's nothing. How about our rate of recrystallization? Also 0. So in an unsaturated solution, it's like you're trying to get to equilibrium, but you never quite succeed because there wasn't enough solute present. Okay? You are not going to have to draw this graph. Okay? It's just there to sort of illustrate to you. It's like, yeah, we're dissolving and then we ran out of solid. Or if you had enough solid, then the graph will continue until you reach equilibrium, just like we saw up there, okay? So if we have enough solid, the rate of dissolving will finally equal the rate of recrystallization. And at this point, this solution is now saturated. Is this solution saturated? No, this is not saturated. Now we hit a saturated solution, and that contains the maximum amount of dissolved solute. If there is any undissolved solute present, the system will be at equilibrium. So now we've hit a point, you can see with our little diagram here, there's a lot more dissolved ions. Compare that with the picture back here. What can you say about the number of free ions? There's a lot more in our second picture. So this is now full of ions. And for every particle that dissolves, these are our red arrows, 1, 2, 3. Another particle recrystallizes, 1, 2, 3. And it doesn't matter whether you call it recrystallization or precipitation. Either of those are fine. Okay. So how do we make a saturated solution? We talked about this last day a little bit. Method number 1, I call it dump and stir. This is not an official name. It's just very descriptive. You dump some solute into water and you stir it. If it all goes away, you will dump more in and stir some more. And if it all goes away, you'll dump more in and you'll stir some more until what?
Something happens until recrystallization.
So I dump some in, I stir it, and all the solute is gone. I only see a clear solution with nothing else in there. Am I saturated yet? No. I dump some more solute in. I stir it around. It all goes away. Am I saturated? No. I dump some in. I stir it around. All of a sudden, I'm saturated. How do I know I'm saturated? There's something left. There will be solid left over. Okay? So you dump some in and stir, and you repeat until some solid remains. That some solid remaining lets you know the solution is saturated. You have the most ions possible. You have the maximum amount of dissolved solute. You can keep adding. What will happen if you add more solid? So you've added some, you've stirred it, you've added some, you've stirred it, you've added some, you stir it. Oh, there's some solid left over. What happens if I add more solid? More solid is just there undissolved. And if I add more, I just have more undissolved solid. It does not affect the concentration, okay? Yes. If you have more undissolved solid, what has happened to the surface area? So you go from having a small pile of solid to having a bigger pile of solid We have more surface area. What does that do to the rate of dissolving? Therefore, the rate of dissolving has to increase. But if the solution is already full, what also has to happen to the rate of recrystallization? Yeah, it's going to go up as well by the different amount or by the same amount? By the same amount so that it remains at equilibrium. The concentration will remain the same. Therefore, we are still at equilibrium and the concentration remains the same. This is a question that, if it comes up, students generally do very poorly on. They're like, oh, I added more solid. That's going to shift it to the right. And now I'll have more dissolved. No, why does that not work? Generally, when I increase a concentration, it will cause a shift. Why does adding more solid not cause a shift? Solids don't have concentration, so you cannot increase the solid. Okay, but you should be able to talk about the rate of dissolving and the rate of recrystallization, both increasing when you have an increase in the amount of solid, okay, due to the greater surface area. Alrighty, so if we have this solution here of calcium fluoride, CaF2, if the concentration of CaF2, sat, what does that mean? Saturated. If that equals 2.0 times 10 to the negative 4 molar, what is the concentration of calcium? Same thing, 2.0 times 10 to the negative 4 molar. And what is the concentration of fluoride? 4.0 times 10 to the negative 4 molar. Hopefully that should be really familiar to you because you did some questions like that on the homework. Did you do those questions?
Where do you get that? I see.
Okay, so we are told that the concentration of CaF2 is this. Oh. It's on page 31. Let's make sure you have a good book. If not, we'll get you a different book. Oh.
It's not there.
Okay. Yes, it is.
No, wait, no.
It's right beside the beaker.
The equation, oh, I'm sorry.
That's okay. Don't worry. It's early in the morning. I have trouble early in the morning also. Okay, are we okay with where we got the 4.0 times 10 to the negative 4? Anyone want to go through that? No. Okay. So If we were to write the equation for this situation, would we write a precipitation equation or a solubility equilibrium equation? Which one? Probably. We probably want to find KSP. Also, we're not talking about precipitating anything. Remember, a precipitation occurs when you mix two things. Did we mix two things? Did we mix two different chemicals? No, we just put the one substance, the calcium fluoride, into the water. We dump it in and we stir. And what that means is if we dump it in and stir, then this will be a 2-to-1 ratio. Or a 1-to-2 ratio. Anytime we had only one compound, this is dump and stir. And the concentrations are proportional to the coefficients. Okay, the ion concentrations are proportional to the coefficients. Is coefs enough? Okay. All right. So yes, you could find your Ka at this point. You would write, or sorry, not your Ka, your KSP at this point. You could write KSP equals calcium times fluoride and plug that all in there and you'd be good to go. Here is a second definition of a saturated solution, which kind of works a little bit better if you have a precipitation that causes a saturated solution. Better when a precipitation reaction causes the saturated solution to form. So rather than saying it is the maximum concentration of solute that we can dissolve, which implies we dumped in some solute and tried to dissolve it, we dumped it and stirred it. Now we're defining it as a dissolved substance is in equilibrium with some undissolved substance. And we can have that happen without, say, dumping calcium fluoride into the thing. We could dump in calcium nitrate and sodium fluoride. Okay, and make a solution that is saturated in calcium fluoride with actually putting calcium fluoride into solution. So this is the method 2 of making saturated solutions. And I call it the mix and match method. Again, this is not an official term. And the key here is that you have two solutions, two different substances. So for example, we might have calcium nitrate plus sodium fluoride. Now, if you put those together and you get a precipitate, so if the two ions match, and which two ions are we talking about in this case? Maybe the calcium and the fluoride. We get a precipitation, and we would get calcium fluoride, CaF2 solid, and that would be our match. So we're mixing the calcium and the fluoride, and they are matching to form a precipitate. And then, of course, you'd have your other thing, NO3 solid. You'd have to balance it, whatever. We're not going to worry about that. You will still have small amounts of the ions dissolved in the solution. Those ions will be present at their maximum concentration. So there will still be a little bit of dissolved calcium. There will still be a little bit of dissolved fluoride. But because they came from two different places, do their concentrations have to be 2:1? No, it could be any amount. I could put in a very small amount of fluoride, but as long as I put in a lot of calcium, I can get the fluoride to precipitate. Or conversely, I could put in a small amount of calcium and add lots of fluoride until it precipitates. So they don't have to be 2:1, okay?
That would be to like add excess amount.
Yes, that's when we added an excess amount. Yeah. We weren't looking at it so quantitatively, but yeah, exactly the same sort of thing. Okay, so these ions, you will still have a small amount of ions present. So these ions will be present at their maximum concentrations. That should say concentrations since they will be different. But they need not be present in proportion to the coefficients. So we are going to take a solution of sodium chloride, NaCl, aqueous, and we are going to mix it together with some silver nitrate, AgNO3, aqueous. And you can see that in situation A, if you actually go through and you count up all the sodiums and you count up all the chlorides in that beaker, you have 8 sodiums and 8 chlorides. If you count up all the silvers and all the nitrates, you have 5 silvers and 5 nitrates. Okay, it just so happens I've made the silver nitrate less concentrated than the sodium chloride. Now we're going to pour them together. We're going to mix. And we get the match, which is our precipitate. And you can see we used up 4 Ag pluses and 4 Cl minuses. They reacted 1 to 1. Yes? Because there's no way to have 2 silvers react with 1 chloride. Okay? One, two, three, 4 chlorides are left over. That's our excess. And we have 1 silver. And that's because this is a low solubility compound, still contains a little bit of the dissolved ions. Is there the same amount of chloride and silver? Are they 1 to 1?
No.
No. The silver and the chloride dissolved are not 1 to 1. So remember, when we put the 2 together and they precipitated, they reacted 1 to 1. The silver and the chloride reacted 1 to 1, but the dissolved leftover silver and chloride are not 1 to 1. What would our KSP be for this particular beaker? KSP of AgCl equals what? How would we write the expression? Concentration of Ag plus times the concentration of Cl minus. And what is the concentration of Cl? Concentration of Cl is 4. And the concentration of the Ag is 1. So that's going to equal 1 times 4 equals 4. And now we're going to take 2 different solutions of different concentrations of sodium chloride and silver nitrate. So this time, instead of having 8 sodium and 8 chloride, we are going to have 6 sodium and 6 chloride. And instead of having 5 silver and 5 nitrate, we're going to have 6 silver and 6 nitrate. Okay, and now we're going to mix them together. We still get the match. The precipitate. But this time, instead of having 4 chlorides left over, we're going to only have 2 chlorides left over. And we're going to have 2 silver left over. Is this 1-to-1 ratio a requirement of mixing those solutions, or is it just coincidence because we happen to mix the perfect ratio? I don't know why. The word that comes to my mind is preordained. Do you know what I mean? It's like that's how it has to be, you know? Or is it coincidence? Based on how much based on our concentrations we used. Have a chat about that with your neighbor. Okay, so we're going to have option A, preordained. Okay, has to be. I wanted that to be in red so it stood out. Let's make that red so it stands out. Option A, preordained, or option B, just coincidence based on the solutions we used. If you have forgotten, A looks like this. You put your fingers on your palm and your thumb by the side, and that is the letter A. If you've forgotten B, you put your fingers in the air, you put your thumb on your palm, and that is the letter B. And the universal sign for I don't know, this is not in any official sign language, is this. Okay? So do we like A or do we like B, or we don't know yet? And it's perfectly fine to not know yet. There's A, there's B, and there's I don't know yet. Okay, we got some B's, we got some I don't know yet, we got some A's. All right. Was the ratio over here 1-to-1? No, because we use different concentrations. So did the ratio over here have to be 1-to-1 because Ag reacts 1-to-1 with Cl? No. So it is not preordained. It is just a coincidence based on the solutions we used. Does that make sense? Because over here, not 1 Ag to 1 Cl concentration. Okay, all of this just goes to show that if you take two solutions to make your saturated solution of silver chloride, if you use two solutions to make your saturation of silver chloride, the concentration of the ions will not be proportional to the coefficients. Do we remember that little symbol? Not proportional to. The little fish is proportional to. Okay? So every time you encounter a math problem in this unit, you are going to have to decide, did we take some solid salt, dump into solution and stir it, and did that make it our solution? And in that case, we do have ion concentrations proportional to the coefficients. Or did we mix and match two different substances, in which case the ion concentrations will not be proportional? Could somebody grab the door? We've got noisy people outside. Just, thank you, Ronia. Just slam it in their faces. I'm just kidding. You don't have to slam it. All good, thank you. All right. So we already actually did this. Our KSP over here was silver times chloride. And the silver was 1, and the chloride was 4. And that gives us a 4. In our second situation, our KSP still equal to silver times chloride. But because of coincidence, it just so happens that we have 2 silver and 2 chloride. So our KSP is still 4. It's still the same. It doesn't matter whether you make the solution saturated by forming a precipitate or by dumping in the low solubility substance and stirring it. Remember, in an equilibrium, the KEQ, or in this case, the KSP value, is always constant unless you change the temperature. Remember, in an equilibrium, the concentrations, do they have to be equal or do they not have to be equal? They do not have to be equal. So when you are mixing two different solutions, the ion concentrations will not be in proportion. to the coefficients. This is our mix and match scenario. On the other hand, if you have a single solid dissolved in the water, the ion concentrations will be in proportion to the coefficients. This is our dump and stir method of forming a saturated solution. And like I said, every question you're going to be asking yourself, was this a single substance or was this two substances? That way you won't accidentally make things proportional that shouldn't be proportional. So there's some questions here. We'll let you do those for homework. And we are going to move on to solubility and Le Chatelier's principle. Oh, Le Chatelier, our good friend. Please remind your neighbor what Le Chatelier's principle says. Everything in there is great. Thank you. Okay, what is Le Chatelier's principle? What does it say? What does Le Chatelier's principle say? I should unlock the door. A system at equilibrium. If a system at equilibrium yeah, or we can say it that way. A system at equilibrium will stay at equilibrium unless it is when stressed, the system will shift in order to do what? To minimize that stress. And remember, this is like not a real explanation. A real explanation would always be done in terms of rates. But you can use Le Chatelier's principle to explain. Okay, our definitions of solubility, the maximum amount of solute that can be dissolved in a given volume of solution. It is also, the second definition of solubility is the concentration of a saturated solution. So if you have the maximum amount of solute, you have a saturated solution. The amount of solute in a given volume is the same as the concentration. So does it make sense that those two definitions are actually saying the exact same thing? Because if we say the maximum amount of solute, we're saying we have a saturated solution, right? So these two parts here. And then we have the amount in a given volume. What is amount in a given volume? Concentration. So they're actually saying exactly the same thing, just different wording. Yes? Okay. Don't get too wound up about that. If you have to define solubility, you can pick one of those. All right? Using the above information, what are some units of solubility? Capital M, yes. How else could we write that? Moles per liter. What else could we use as a quantity? As an amount? We could use grams. Grams per liter. Grams per milliliter. Milligrams per milliliter, etc., etc., etc. There's all kinds of them. But out of all of those, we will mostly use molar solubility. And what is the unit of molar solubility? It's really obvious. Moles over liter. Occasionally, you'll be given values in grams per liter like you were with the homework, but you will usually change them into moles per liter. Now, according to Chemistry 12, in our data booklet, let's go, everybody grab their data booklet and turn to page 4. I think it's 4. So for all of our compounds here, if we are going to use this table of solubilities, soluble means you can form a solution with greater than or equal to 0.1 moles per liter. Okay? No, I'm not going to mention that right now. We'll talk about that later. So there are other definitions of solubility. Back when the AP people used to have to memorize their solubility rules, the definition for AP was 0.01 moles per liter. So it is arbitrary. Do you guys know the word arbitrary? Arbitrary means we just set it somewhere because it's kind of maybe convenient or something like that. It's like setting 0 degrees Celsius at the freezing point of water. That was an arbitrary decision. Convenient, but not necessary. We could have set 0 as the boiling point of water, right? 0 Kelvin on the, do you guys know the Kelvin scale of temperature? Okay, Kelvin is not arbitrary. 0 is literally where there is 0 motion of the particles. So that wasn't arbitrary. That's like, temperature is a measure of the average kinetic energy. And if you have no motion, you have no kinetic energy. So that's 0. Okay, anywho, this dividing line here, where we say, if we are right at 0.1, anything above 0.1 is considered soluble. Anything below 0.1 is considered low solubility. And that's why when you see questions, you will often see 0.2 molar mixed with 0.2 molar. And we're going to mix equal volumes. And the reason for that is, anyone see the reason for that? Why we're using equal volumes of 0.2 and 0.2 to ask if a precipitate forms? Anybody remember what happens to concentrations when you mix volumes? They dilute. Yes? And if you mix equal volumes, what happens to any concentrations? It'll dilute the same amount. Okay, let's do the math on it. Okay? So here, our concentration of silver, we have 0.2 moles of AgNO3 in 1 liter. So I'm going to actually draw that as 2 little circles. Okay? There, it's dissolved. 0.2 moles of AgNO3 in 2 liters. So the concentration of Ag is, actually, no, I'm not going to do that. That's terrible. I'm just going to write Ag plus, Ag plus. What's the concentration of Ag plus? Zero 0.2 molar, yes. 0.2 molar. And over here we have 0.2 moles of NaCl. We're worried about the Cl in 1 liter. So we have a Cl minus and we have a Cl minus. What is the concentration of chloride? 0.2 molar. And now we are going to mix them together. And before any precipitation occurs, we have Ag plus and, no, I'm not going to draw those in. It's just making it messy. We have 0.2 moles of AgNO3 in 2 liters. What's the concentration of silver? 0.1. And we also have 0.2 moles of Cl minus in 2 liters. What's the concentration of chloride? Also 0.1. And what is magical about 0.1? Any substance listed, not yet, thank you. Any substance which is listed as low solubility on the page 4 chart will precipitate. So, if I was to give you 0.1 molar and 0.1 molar and we mix them, equal volumes, you would have 0.05 molar and 0.05 molar. And you couldn't tell from that chart if a precipitate would form because at 0.05, maybe you would get a precipitate and maybe you wouldn't. The chart does not tell us at a lower concentration whether you'll get a precipitate or not. You would have to do some KSP calculations. Okay, so, but if you see this 0.2 and this 0.2, 0.2 and 0.2 in equal volumes make 0.1, and that means that you can use page 4 of the data booklet. Okay. It is possible, and we just talked about this, it is possible to mix silver nitrate and sodium chloride at low enough concentrations that a precipitate does not form. And we will learn how to do that when we get more into the math. Okay. How can we change the solubility? What is solubility? Tell your partner, what is solubility? The what kind of amount? Maximum. Amount of what? Solute. Okay. That can do what? Dissolve in a given volume of solution. Okay. Consider the following equilibrium. Calcium hydroxide solid in equilibrium with calcium and 2 hydroxides. If we increase the solubility, does that mean we can dissolve more or we can dissolve less? If we increase the solubility, we can dissolve more. More solute can dissolve. And if more solute can dissolve, are we shifting that equilibrium to the right or to the left?
Depends which equation. Oh, no, it's a solubility.
It's a solubility, so we're looking at the solubility equilibrium equation. Do we want this to shift to the right or to the left if we want to increase the solubility? Talk with your partner about that. If we want more solute to dissolve, is that going to need a shift right or a shift left? Do we need a shift to the right or do we need a shift to the left? Everybody. I heard one person. Okay, you know what we're going to do? Right. Cross your fingers. That's for R. Okay, that's an R. Left, L. What do we think? Right, left, or I don't know yet? Got lots of rights. Okay, yes, because this direction is dissolving. Okay, going to the right is dissolving. So we need a shift to the right to dissolve more solute. So if we shift the above equilibrium to the right, we will be dissolving more solute. And if we dissolve more solute, what is happening to the solubility? If we dissolve more solute, do we have more than the maximum amount, or do we have less than the maximum amount, or do we just keep the amount the same? Okay. Solubility. Another way of saying solubility is to say the concentration of a saturated solution. Yes? If we dissolve more solute, your homework is page 34. We'll talk more about this next day. You are welcome. Bye. Yes. That's fine. Electrolytes, electrolytes. Here? It's here. I'll get there. Sorry, I swallowed tea the wrong way. It'll teach me to talk while drinking. Like, should not do them at the same time. There you are. Hi.
What unit is this?
Solubility. Well, this is acid base, but they're on solubility.
The easy part or the hard part?
The easy part.